Well, how's everybody doing out there? Welcome to Chapter 7, which is confidence intervals, and this is also the beginning of our inferential statistics. So, pretty much from this point on, everything in statistics that we're going to be working with is trying to make some kind of a claim about our population mean or population proportion. And so, in fact, in this section, what we want to do is learn to use our sample mean as a way to estimate with a certain certainty that our population mean will live within this interval that we're going to form. So again, if we kind of look through some things that we're going to need to know to do these kind of stuff, are a couple definitions here. So our point estimate is going to be the single number that estimates a parameter. So for us, what we're going to be using for our two different point estimates are either going to be our sample mean, if it's a mean problem, or our sample proportion if it's a proportion problem. And again, with the whole goal of trying to estimate exactly where our population mean is going to live. So we're not going to say our population mean is this number exactly, but we're going to be able to say with certain confidence that our population mean lives between this value and that value. All right. So our confidence interval, again, is going to be centered around our sample mean or sample proportion. And again, we're going to use it as a way to estimate where the population mean or population proportion actually lives. And so we're going to be practicing with some different confidence intervals, but typically the ones that occur most often are going to be 90%, 95, and 99%. But again, there can be other ones that come up as well that we'll be working on. And so again, why do we use confidence intervals? So first off, it gives us a lot more it makes the data seem a lot more realistic. So, like if you look at these two statements, for example, the first one is I think the average width of our iPhone cases is 67 millimeters, or I'm 95% confident that the average width of our iPhone cases is between 66.8 and 67.2. So, again, it's kind of hard to narrow something down exactly and say that it's always going to be exactly this width. But having a little bit of a plus or minus or a little error factor makes it seem more legit and more likely that those values are actually going to live in that space that we're looking for. All right. So another piece of information that we're going to be talking about is our degree of confidence. So it's the degree, the probability of 1 minus alpha, that the relative frequency of times that the confidence interval actually does contain the population parameter, assuming the estimation process is repeated a large number of times. So again, think about our central limit theorem when we're doing these guys. And so again, our confidence intervals that we'd be looking for would be our 90, 95, and 99. And so the alphas that would go along with these would be alpha equals 0.10, alpha equals 0.05, or alpha equals 0.01. So when it says 1 minus alpha, that's what it is in reference to in that case. And so the alpha is actually going to represent the area under the curve of the bad space, the space that we're hoping that we don't live. So these are going to be on the extreme left and right of our normal curves, which we'll see in a little bit. All right, so last thing that we've got is our critical value. So it's going to be the z-score that actually separates the good value from the bad value, from where we want our population mean to hopefully land compared to where we don't want our population mean to actually land. And so what we do is we use this idea of calling it z alpha over 2. And the reason being is if we look at our normal curve, say for example, and we're looking for a 90% confidence interval, so if I draw from here to here, I've got my 90% confidence interval, then the alpha is going to be this part that's shaded. And so both sections added together is going to equal 10%. But if I divide them by 2, then I see that each section is 0.05. So that's why we're calling these z alpha over 2. So it's the z-score related to the alpha divided in half. So, all right. Any questions about the definitions, just let me know. So in the meantime, let's talk about how we're going to construct our confidence interval and what things are necessary in order to be able to do this. So first thing, and this is true of pretty much all of statistics, the sample has to be a simple random sample. If it's not, I mean, it's not even worth doing statistics on. And so at this point, we shouldn't even really need to list this anymore. So in this section, notice we're estimating the population mean where the sigma is known. So the population standard deviation is given. So this is going to be a pretty rare case, but it's a good case to start off with. So we definitely need to know the population standard deviation, which again is rarely going to happen. So the more realistic case is going to be 7.2, but at least this gives us a nice introduction into what we're doing. And then the next most important part is the population either has to be normally distributed or n is greater than 30, in which case we can use the central limit theorem to make sure that we do actually have a normal curve to begin with. All right, and so this word unusual is coming up again. So in the context of this problem, it may not always be that 5% that we've been using in the past. It's going to be based on whatever confidence level we're working on and whatever alpha level we're working on. And so again, looking at our nice normal curve that we've got drawn here, we know because of the empirical rule that 95% is about a z-score of -2 to 2. So the blue area is going to be our confidence interval that we're hoping the population parameter lives in. And then these two white sections are going to be the bad areas. So these are the two places where if the population mean lands there, it can happen because again, it's not 100%. So the bad areas, so the population mean could live in these different bad areas. And again, that can happen, it's totally fine. But that's where the bad areas are going to occur, on either high to the right or low to the left as we go along. All right, so let's take a look at an example here of how we can set up a confidence interval using this 95% confidence interval that we've got. So we've got a sample of 50 students, and we get a sample mean of 23 with the population standard deviation of 10. Find the 90% confidence interval for the population mean. All right, so let's write down everything that we know first. So we know our n is 50, our mean is 23, our population standard deviation is 10, and our 95% confidence level tells us that our alpha is 0.05. And in this case, we're going to assume the empirical rule and use our z-score of 2 and -2 for this one to set it up. All right, now when we're setting up one of these problems, what we're going to do is we're going to find the upper bound for our confidence interval, and then we want to find the lower bound for our confidence interval. So the way we find our upper bound is we're going to take our sample mean plus our z-score times our sigma, all divided by the square root of n. And so our sample mean is going to be 23. Our z-score in this case is 2 times our sigma, which is 10, divided by the square root of 50. All right, so let me type this in the calculator real quick and see what we get. So 23 plus 2 times 10 divided by the square root of 50. All right, so our upper bound looks to be 25.83. So for these, I usually round to like 2 decimal places. So my upper bound is 25.83. Oops, sorry. Didn't write the first time. 25.83. And then for our lower, the only difference is instead of having the plus, we're going to do a minus. But everything else is going to be exactly the same. So it's going to be 23 minus 2 times 10 over square root of 50. And so on our calculator, the nice thing is we can actually just pull up what we wrote and just go ahead and change this plus to a minus. And so it looks like it's 20.17. All right, so we've got our lower bound is 20.17. And so the way we want to write this, again, since we're trying to estimate the population mean, we want to write this as an interval with the mean as the variable in between our inequalities. So this is going to look like 20.17 less than mu, less than 25.83. And so in words, what this is actually saying is that we are 95% confident that the population mean will be between 20.17 and 25.83. All right. So that's exactly what we're trying to do. Again, our goal is using these different percentages, trying to figure out what our confidence interval might look like in order to guarantee that our population mean lives within these different values and stuff. All right. Any questions about that one? Just let me know. All right. So again, just to kind of go through the same thing we did above, just so we can see what it looks like. So when we're trying to find a confidence interval by hand, there's of course some certain piece of information that we need to know. So we do need to know the sample mean, of course, because that's going to be our middle of our confidence interval. We need to know the population standard deviation divided by the square root of n with our central limit theorem. And then we need to know the corresponding z-value that goes along with that z alpha over 2. And then in formula form, we've got our formula looks like this. So this is all written as one big step plus or minus. So this is the same exact thing written out in expanded notation using our mu as the center. And then if you take the z-score times the standard deviation, all this kind of stuff here, this is actually what's known as the margin of error for the problem. And so if we write it as just the sample mean minus the margin of error, it ends up looking even cleaner and looks kind of like that. All right, so again, that's exactly what I did above, and so we'll want to be able to do the same thing. So the two things that are going to be easy about what's given is the sample mean is always going to be given, and the population standard deviation is always going to have to be given. But the z alpha over 2 is not necessarily going to be given. So we will give us the confidence interval, but we're going to need to figure out how to find that z value. So let's talk about that, because if we don't get that right, that's of course going to mess everything up from there. So how do we figure out this z value? Well, luckily we've got our calculator, and what we're trying to do is we're trying to find the z value that associates with a certain probability. And so if you remember from last time, that was our nice inverse norm command, allowed us to do exactly that. So with this one, let's say, for example, we wanted to find the z-score associated with a 90% confidence interval. So first thing we need to recognize is if we've got a 90% confidence interval, then our alpha is going to be 0.10, which means both of those blue sections added together are going to be 0.10. So if I divide them by 2, then my alpha over 2 is going to be 0.05. So I've got a 0.05% on the left, and then a 0.05 on the right. All right. Now the good thing is the z-scores that we're finding are on the standard normal curve. So we're using a mean of 0 and a standard deviation of 1. So they're both symmetric. So when we find, say, this lower z-score, the only difference for the upper one is it's going to be the positive version, not the negative version. So if I want to find this left z-score, what I want to do is just type in inverse norm, my 0.05, and then again, we're using our standard normal curve for all these. So we're going to use 0 and 1 for our mean and standard deviation. So let me flip over to the calculator real quick so we can find that z-score. So second vars, inverse norm, 0.05, comma 0, comma 1, gives us a z-score of negative 1.64. And so again, let's make sure we round these to 2 decimal places as well. So that means on our picture, this first one is going to be negative 1.6. And since our standard normal curve has 0 at the middle, this upper one is just going to be positive 1.64. All right. So I'm going to have you guys do the same thing for practice 1, where we find a 98% confidence interval for these guys. And then we'll come back on the next video and go over a little bit more stuff here. So let me stop here and let you guys work on practice one.